Am I visible? Hello, everyone. Welcome to another session of Introduction to Machine Learning. And as suggested by Somil, for today's session, I'll be handling unsupervised learning. And for the next other two sessions, the sessions he have suggested for graphical model, I would like to deal with that. So I'll look into that as well. So, continuing with the unsupervised learning, although I've already discussed one algorithm from unsupervised learning, which is k-mean clustering. So, again, apart from k-mean clustering, I'll be handling some more unsupervised learning algorithms. So, before that, I would like to share the collab link. Yep. And along with that, I'll share my screen. So, just confirm if you're able to see my screen before I can proceed. Yeah, so my screen is visible, right?
Yes, ma'am, your screen is visible.
Okay. So if you guys have any question, again, the same thing, please let me know. So starting with the basics of unsupervised learning. So what do you mean by unsupervised learning and how it is different from supervised learning? Unlike supervised learning, where we have data already known, like the label data, which means in a very simple language, if I say, I already know that this kind of pictures belong to dog category and this kind of pictures belong to cat category. That is what supervised learning is. Okay. But in unsupervised learning, we don't know what this feature means. That can be a cat, that can be dog. So we don't have a label data. Okay, or we can say the ground truth, we don't know about unsupervised in unsupervised learning. So how we do it? Based on similar features. For example, if we have to identify between a cat and dog, so we know what are the features that can differentiate them. Okay, so firstly, we will start putting all the similar features into a clusters like eyes or four legs or a tail, something like this. Then we will start segregating in the terms of dissimilarity. And then we form a cluster and then we do the classification. And then when an unknown data which needed to be predicted, we will see like the data which has been provided or the unknown data which we need to classify which, which among the clusters that we have classified is the very much closest. That is what we do with k-means, right? So, in simple terms, if I have to tell you, unsupervised learning, it's something mathematically like in unsupervised means we have input variables, but we don't have output variables. That means we don't have label data. In very one line, I have to tell that if the data set is labeled, it is supervised. If the data set is unlabeled, it is unsupervised. That's it. Okay, so with the term itself, like what supervision means, that you already know what needed to be done, what should be the output. Unsupervised, you don't know, you don't have a label data, you don't know what that feature is. So this is one example I would like to show, like this how supervised learning is. We already know these are two distinct features, a red cross and a circle. So we are able to draw a boundary and do the classification. But in unsupervised, all the data sets are circular only, right? So we are making a clusters based on which are very similar to each other. Which means if I have a picture of an image where we have grass and water body, for example, just two features are there, so the pixel values of grass will be very similar to will be very different from the water pixels, right? But the pixel value, one pixel value of a grass features will be similar to the nearby grass features, right? So in terms of that, we do a clustering. Okay. So moving ahead, I'll take some examples. I have taken few unsupervised clustering examples, and I don't know if you have heard, like you have, apart from k-means, there are other clustering algorithm as well, which I have considered for this example. So I've taken some theory basis for that as well. So let me know if you have not heard about it. I can go in detail. Otherwise, I will just give an overview of those clustering algorithm. But before that, let's see how we proceed with unsupervised learning algorithms. Okay, how we do classification for unsupervised learning. So the data set I've considered is iris data set, where we have to make a predictions. Okay, and in this we have four attributes which we are considering: petal length, petal width, sepal length, and sepal width. Okay, and we need to classify three classes, which is, these are the classes, you don't need to get into this, these are scientific names: setosa, virginica, and versicolor. These are the names, the scientific name of the iris. Is basically a flower data set, different species of flower. So how do we identify different species of flower based on these four attributes? And those attributes are petal length, width, sepal length, and sepal width. That's it. Okay, so, okay, let's begin with that. Okay, so the first thing we need to do is we need to import our all the libraries. So again, all the libraries are known to you: matplotlib to plot, sklearn to import your data set, matrices, pandas, and numpy. These are like very basic libraries which we have used from last 10 weeks. Okay, okay. So yeah, we are loading the dataset dot load iris. Now we have to know the target names. So this is the species dictionary which we are taking, and we are telling the to take the target names of the iris dataset, which we have already discussed, that the four attributes which we need to take. So we need to take their value points, right? Yeah. And now we need to see what are the data sets available for that iris.data. So if and while I'll run, this is the array which I'm getting. So, why this is coming like this, I'll tell you. Because now this I have not converted into pandas. What does pandas do? It gives a proper, data frame. So right now it is more of like 5.8, 2.6, 4, and 1.2. So these are the species name, the four attribute, the petal length, petal width, sepal length, and sepal width. This is the values. That's it. Okay. So yeah, now I'm giving my features name. So I know sepal lengths, and like this is the parameters as well, in which unit it is there. So I wanted to know what are the features. So the first the row which is showing is sepal length, the second is sepal width, the third is petal length, and the fourth is petal width. Now I need to know what is there for my iris target. So 0, 1, 2. So we were having three classes, right? If we'll go back, this is where I have defined it, right? Okay, yeah. So my four attributes, oh, where it is not showing. Yeah, yeah. So my four attributes were these things which I have discussed, and my target class. Target class are these three iris classes. So that is why it is 0, 1, and 2. So 0 means setosa, virginica is 1, and versicolor is second. So this is just the data set description which we are playing around. Okay. So yeah, see, target names have also been given, right? Now I need to do in the form of data frame. So I'm calling my pandas pd.data frame, where I'm calling my features or attributes, and for y I'm giving my targets. Okay. Yeah. Now I need to draw a plot where I need to see how my x and y levels, or I need to see the scatter plot of sepal length and sepal width, petal length and petal width. So I'm drawing a scatter plot. See, now we can see the two classes. So this is for sepal. So sepal length versus width, you can see the classes, and petal length versus width, you can see the classes. So these are the dots which are representing, each dot represent one value. So the values which we got above, right, for all the four rows and columns, so that is what it is being represented. Yeah. So instead of doing this all stuff like in one by one, which I showed you, in a very concise way, you can do the same. So this is what I wanted to show. Just the steps which right now I showed you can be printed or can be commanded in just one single few lines, which is like this. Imported some modules like data sets and plot, loading the data set, printing the methods which has to be done on data set, features dot feature name, which is like all the four features name, targets dot iris underscore dfi, iris underscore df, because this is where my data set has been loaded. So iris dot underscore df dot target names, labels. So I need to print it. So for 0 I'm giving red, for 1 I'm giving blue, so 2 I'm giving green. Over here you're not able to differentiate, like it's not differentiable because every all the data points are in blue. Now I'll show you all the three target names you can identify with the different colors which I have mentioned. X-axis is my sepal length, y-axis is my sepal width. Okay, and now I'm drawing my, this is in one way you can do that. I'm drawing my scatter plot. Now see, this three targets are there, right? So I have given the colors, right? Red, blue, and green, right? I don't know why it is not coming red, blue, and green. Maybe some color issue or something. Okay, forget about that. So I have this thing, right? uh, these three colors, at least you can understand. You don't know, okay, for example, now you don't know which is setosa, versicolor, or virginica, but at least you can know these three classes, which are the three classes and how they are like distinguishing each other in the form of clusters. Over here we can see some overlapping, right? So that is how we will do, and we will do the classification further. So this is just one representation I wanted to show, that instead of writing 20 lines of code, you can also concise it in 5 or 7 lines of code. Moving ahead. Now, one very important concept I wanted to discuss, which is called principal component analysis. Again, I'm doubtful that if you have learned this in theory classes, but principal component analysis is one of the very important terminology that comes when we go for, especially when we go for image processing in any sense, when we go for like these supervised learning or unsupervised learning, when where their images are involved, or even the higher data sets available. So what does principal component analysis means? So it's actually a methodology, principal component analysis, which whose aim is to reduce the dimensionality of data. What does it means, dimensionality of data? So for example, you have thousands of data, but just starting 100 of data is the information which is sufficient to identify your object, or to do the classification for your data set provided. The remaining 900 informations are not required. So your question would be, how can that be possible? So very basic example if I have to tell you, for example, if you have to identify between a cat or a human, so the very basic information would be like, we have two legs, they have four legs. So the features, one features which we can identify at least between that we human and a animal, or not specifically cat, animal or a human, is this thing, right? One very specific with the visualization factor. So other informations may become irrelevant in that sense. Okay, so this is how it is, it is very basic example. It may not be relevant, but I'm just wanted to give you a idea that how this 100 data is relevant and other 900 data are not relevant in terms of classification. So there can be example like this. So when we work with a very larger data set in now during this time period, um, memory consumptions is one important factor that deals with this data set. So apart from being a data analyst or being a machine learning programmer, the one very important factor you need to think about is how you can optimize your model, or how you can reduce your dimensionality of the data as well, without affecting the important factors which needed to be taken out from that data. Okay, so this is where PCA comes into picture. So it reduces the dimensionality without even interfering with the loss of information. So what PCA does is, there's something called eigenvectors and eigenvalues, which we read when I was giving you very first lectures of linear algebra. So eigenvalues, or see, any data sets or any images values can be represented into matrices. Matrices are what? The collection of numbers, that's it. So your data is represented in the form of matrices. Okay, those matrices depends on the data set, the size of data set. Okay, so from those matrices, there are so many mathematical computation that has been done. Again, I'm telling you, machine learning is nothing but some mathematical computation going on in behind the coding process, which we do. So this coding is nothing but some mathematical computation going on. So what my PCA does is, it calculates eigenvalues and eigenvectors. Or if you don't want to get into that, simply think about it. It does some mathematical computation, and if we have 100 of data, and the first 20 data itself give 96% of, the values which is required, it will take just 20 bands. I know the 4% accuracy we are, compromising with, but that is where trade off happens. Like, we also want a very good model. We don't want to, compromise with our accuracy, so we go in a middle ground. Okay, if we have to go for 100% accuracy, which will never be the case, but it will take so much of, time to compute that data, or so much of your system memory, and other computational effect will be there. So that is not a good way to do that. So what you do is, you come at a middle.
Madam,
Yeah.
I have a question that suppose I am implementing the PCA for dimensionality reduction. You told that we are looking for low loss of information.
Yeah.
If someone asks me that how you will say that you are after the dimensionality reduction the information loss is low, how to prove that? Any
That
idea you have?
Yep, that's what I'm telling. That's how I will show you the
Okay.
example, how
Uh,
we decide that this, after applying PCA, this much information, or this much data we you have to take. So there's something. First, PCA what does is, it,
okay.
like, if for example, if you know what correlation is.
Yes.
Yeah, exactly. There is where PCA works on. So what it does, if we have hundreds of data, it sees that all the hundreds of data, how many of these data have correlation with each other. We don't need redundancy in our data. If all the data, in above all the data, if 60% of the data have correlation, there's no need to take them. It's more of like, if you have to make, pairs, you have one, two, three, four classes, you need to make pair of them. So you can make 1 and 2, 2 and 3, 3 and 4, right? Again, you can make 1 and 4, but there's no point of making 4 and 1, because 1 or 4 or 4 or 1, it's the same thing, right? So that is
Yes.
correlation. You're getting my point, what I'm trying to say?
Yes. Yes, ma'am. Yes, ma'am.
Exactly how PCA works. So that is what I'm saying. If I give you this 4 number, and I told you, give me like, on, you have to make two pairs from these numbers, but they need not to be repeated. So you will make 1 and 2, or 2 or 1, either of them, right? You cannot make both of them, because it doesn't make any sense. So that is how PCA works. It reduces the dimensionality by detecting the correlation between variables, that's it. And then it reduces the dimensionality. Okay.
Okay.
Yeah, so I'll just show you. I'll show you how PCA works and how we take it. I have
Ma'am, again, I'll interrupt you. That I means in my research work, one of the person has asked me the question: how you mathematically explain that you reduce the dimensionality without loss of information? So that part I
so
actually
you
look
yeah
for. So
so you need to calculate the variance. What you can do is,
okay,
just
Huh.
calculate the variance of your data. And when you will
Mhm.
calculate the variance of your data, you can see how much like the moment you will calculate the variance of your data, you will get to know that 96% of the variance comes in 20% of your data. So you
Okay.
can say ki, okay, like 96% of the variance or the maximum variance lies in this part of the data, so why I need to go for another part of the data? That's it.
Okay. Okay.
So
Okay.
it's
Okay.
more of like ki, the moment your data set start becoming saturated, like for example, your if you're working on your data set and the maximum accuracy is coming for starting 20 data sets itself, after that the accuracy is like 0.01 or 0.02, so it will not make much difference, so you can obviously remove them instead of putting them in your data,
Okay.
right? So there's just one
Ah.
thing you need to prove. You have to calculate the variance. You need to calculate.
Variance of the entire data.
Exactly. Variance of the
Okay.
data, and then you need to tell ki, see, this is the variance which I'm getting, and you can see the, so for entire data you will get the variance, right? So you can see like in
Mhm.
starting 20 data or 30 data, you're getting the maximum variance. So you can see, why
Yeah.
do I need to go for another set of data or the remaining set of data when I'm getting the maximum in the starting 30
Mhm.
data? That's it.
Okay.
Okay.
Okay. Thank you, man.
Yeah. Thank you. So okay, so we'll go with this thing. We'll see how my PCA works. So right now I'm doing just the transformation of the data, which is I'm converting my data into standard scalar. Now I'm importing PCA from sklearn, and yeah, scalar. So this is, I'm creating the PC instant. PC is the variable, small PC is the variable, and this capital PC is what I have imported. Okay, so now x norm is the normalization of x which I have done. So I am, I just run this, yeah, okay. So I'm fitting my PCA data with the x normalization. Now I'll show you a graph. Wait, let me run this. Yeah. See, now you can see the things I was telling you. Whosoever asked me, I didn't know your name. So see, you can see the variance, right? I calculated the variance for this data set. Right now, you can see the PCA features and the variance graph. You can see for the zero data, you are getting maximum variance. For one, you are getting this. Two, you are getting this, and three, it is less than even zero point 0.5, not even 0.5. I think I should say 0.2 or 0.1. So 3k baad, either it will be 4, 5, 6, it will be less only, right? So you don't need to take those features. That's it. That This is what the explanation you need to give.
Okay.
So you can say ki because the example I'm showing is a very small data set. It's a very small data set. So in initially only it's sufficient that you can say, you either you can take these two features only, 0 and 1. You cannot neglect one, because pretty much it's a good variance, because it is around one approximately variance it is giving. Yeah, you can neglect two. You can obviously neglect three, and after that, so this is how you can tell ki from this value, I can see my variance is maximum for 0 and 1. And after that, it's just decreasing. So I don't need to take that. Okay. So I have written over here PCE. So I have done this PCA. I have reduced my dimensionality. I was having so many of data. I have just taken, I need to take the two features. So PCA for dimensionality reduction of the iris data set, retaining only the two most important components. Okay, two most is 0 and 1. I can take 3 as well. You can consider, if you have, if you feel like it's not consuming much of your memory, you can take 3, 0, 1 and 2 itself. Okay, anything is fine. Okay, so for this example, I have taken, like over here I'm showing that PC components I have taken 2. So now what my model data is 150 and 2. 150 is my number of, you know, information which is being provided, and 2 is the features which I'm taking. Okay, I have plotted the scatter plot as well for 0 and 1. 0 and 1 only data set I have taken, right? So see, 0 and 1 I have data set. I have plotted a scatter plot. That's it. So I hope I'm clear what I meant with my PCA. So this is just one example I wanted to tell you, because it is very much relevant with unsupervised learning. Because what happened with unsupervised is we don't have a label data, so we try to make as much clusters as we can, so that our prediction is more accurate. So for that, my data set increases vastly. So there need to be some, and there's so many dimensionality reduction method, but the most popular one is principal component analysis. So I wanted to give you an example how you can do that. So this is how you can give an justification that why you have taken just 2 components or 10 components or 20 components based on your variance, and that is what mathematics is hidden behind PCA. That's it. Okay. So yeah, I just wanted to show this the 2 components scatter plot. Now let's get into some clustering algorithm. I have already dealt with k-means. I have taken a whole class on k-mean clustering, both for classification and regression, where you can do k-means clustering and how you can identify how to identify the number of k. Everything I've taken. Over here, I'm talking everything about in terms of unsupervised. There's nothing as classification. There's always for regression. Regression means uh, again and again and again we do clustering with the different values, and we do the classification. So what does k means? Again, the same thing I'll tell. Means average or mean, which we if we have for example, if we have 4 clusters and a data set come which we don't know which cluster it belong to. These clusters are mainly different classes. Okay, class 1, class 2, class 3, class 4 are represented as cluster, and there's a data set which we don't know which class it will belong to. So what we do is we calculate the mean value from of that data point to all the nearby data clusters class, and the least one, the distance between least point or the mean of least point is the data point which belong to the that class. That is what k-mean is. Okay, so again, it's pretty much simple, like sklearn clusters. You're importing your k-means, which is like in sklearn there is already k-means. Okay, and I'm taking n clusters as 3. This k value I'm taking as 3. Okay, why 3? Because this time I've taken 3 because we were dealing with 3 classes, right? You can even increase or decrease it. That's not an issue. That depends on, I have already discussed that how you can define the number of k or the value of k. Okay, depending on 2 factors, accuracy and error. Okay, now I'm doing the x normalization labeling of model, and this is what I did. Okay, so this 1 2 0, you know what are these? 0 represent, we were taking 3 target features, right? I forgot the name. Those target features were there, so these 0 1 and 2 represent that only. So it is telling the clusters which I have taken, where all there are one class, the class which is represented as 1, the class which is represented as 2, and the class which is represented as 0. So that is what it is showing. Okay. Now I need to do the, okay, so over here I'm fitting my predicted data with PCA features. We have already calculated PCA features, right? So I just wanted to see how my k-mean will be done with the PCA features. So I've given labels as labels, species, and which iris species which we're having. So this is something called cross table. Cross table tells you about, so this species is like this row, Sesota, versicolor, vergica. Labels is 0, 1, 2. So this is represented like Setosa is represented as 0, versicolor as 1, and virginica as 2. So this tells about that this 0050 means how many values of 0, how many Setosa values are there in that features, how many versicolor features are there in that. So this is just a reference table which you can compute to know how many values are there, how many data points are there for each target. That's it. Now this is where I'll be like fitting my model, and I will be predicting my a new model, a new data set. Okay, so this is where I'll do that. So you can see, okay, let me go ahead first. Okay, so again, I have done this importing of model again, which is not required. I am like right now I showed you again step by step. like this is more than this is just one cell which is having all the data, like all the columns, so you don't need to do it step by step. That's it. So that is why I've written again that how in one cell itself you can write in 6 7 code, you can do the fitting as well as prediction. So importing of like importing of libraries, calling of my data, declaring of my model, key means this I've already done above, but that is why like step by steps, right? I just wanted to show in a very precise form how you can do. So fitting of model, and this is a step you have to follow. Importing the libraries, loading data set, uh, calling your model, fitting your model, and doing the prediction, and then doing the evaluation. So I have done the prediction, I have done the fitting, and I'm doing the prediction. So these are the value you can obviously change 7.2, 3.8, 3.5. This is something random variable, random numbers I've taken, and these are like sepal length, sepal width, petal length, petal width, and on based on that, it have to tell which category it will belong to. And we were having three categories, right? 0, 1, and 2. Some names we were there as the setosa, versicolor, and something like this, right? So we do the prediction. So this time I have done two prediction. Predicted label, which means it will tell which label it will belong to. One means it belong to what? I think it was versicolor or virginica, either of them. And all predictions means that how this data set will belong to all the three. You can change the values as well. If you want, like let's take it 10, let's take it 2.5, anything you can, or 1.8 and 0.6. Let's take it there. Let's do it. See, okay, again it's predicted level 1. Then let's take it 3. Let's see. Okay, why it is like this? It will change definitely. So if we can say, okay, now you can see predicted label 2, right? So now it belong to the different label, right? So depending on these, this is the predicted label, which is a unknown value, which we don't know. The prediction is being taking place. Okay, so this is called k-means. Now the second clustering method is called hierarchical clustering. So hierarchical means a generation wise. So if you'll take like hierarchy, how is it means your grandparents, your parents, your children, their children, something like this, we make a hierarchy, right? So similar to that, how hierarchy works. So actually if we have a class, so from each class how it is being distributed, I'll show you. I have created a graph as well for that. So for hierarchy, we have something called linkage and dendrogram. Okay, so linkage means how everything is connected, like how you will be connected to your grandfather via your father, right? So that is called linkage. And dendrogram is when we make this chart, right? We make, okay, I'll show you with the graph itself. Wait. Okay, so this blue color line is there now. This is called dendrogram, and this how this is connected from one point to another. So this is called linkage. So we need to import them because that is like inbuilt functions which is needed for hierarchy clustering. Okay, I'm taking the data set. I'm directly calling the data set from the given website, and I have taken this particular data set because sometimes all the clustering method does not work for all the data set. There are particular like you have to change your models as well depending on your data set. And now your question will be how you will get to know. So that depends on your practice. You will definitely get to know, okay, these kind of data set is there, so these kind of model can only work, or this model will not work. So there's something like this. So for this uh, my iris data set which we're working will not work because that data set have different kinds of information which will not work for this hierarchical data set. Okay, so I've taken a data set which is seedless rows, which is none of concern. It's more of like a data set which is having different varieties of grains and different varieties of seeds, and based on that we are doing the prediction. Okay, so we are making the my grain variety is the output, and other than that all the information related to that is my input. Okay, so I'm taking varieties. This is what I'm doing. I'm extracting seed values, and yeah, now over here I'm performing my hierarchical clustering. I'm merging my linkage. Linkage is where it will link both the things. So in linkage I have sample. Sample is my this values which is being taken, and this method is like there are different kinds of methods. One which we take is complete. Complete is like take all the methods and do all the linking. You cannot drop anything. That's it. And then dendrogram, which I was telling, was that it needed to make a graph which all varieties, what all things it needs. So it is taking merging. Merging have this linking samples. Rotations are just like the values which you want. So left rotation 90-degree means this values, this in x-axis the values you can see now. This is the varieties it has done. So I don't know if you can see. Should I zoom it? If you can see, okay. If you see this graph, yeah. So on x-axis, whatever it is mentioned, right, these are the different species of wheat. So it shows that how these are related. These are three classes, and how the other three classes are also related. Okay, wait. Okay, I'll show you. So this blue color linkage is there. It is showing how this blue color linkage is something telling about food, for example, because seeds are for food, right? The another linkage is telling about seeds. The another linkage is so something like this. So we take an example. We take that the how you make a family tree, something like this. Okay, so this hierarchical clustering do the classification based on that. We have information related to seeds. In those seeds we are distributing with for example a particular kind of seed, or a particular kind of seed which grows in particular kind of season. Then that particular season how many seeds are there, and then wheat, and in wheat also different kinds of wheat. So something like this we are doing the hierarchical clustering. Over here, I've given how you can differentiate between k-means and hierarchical clustering. So one important method is hierarchical clustering cannot handle big data. And that is when I told you ki you should know why and which kind of data set requires, or which kind of data set work on which kind of models. So this is where you have to deal with. My iris data is comparatively big with the data set which I have worked for hierarchical. So hierarchical clustering cannot handle big data while k-means can do. So that is why I didn't use my data iris. Okay, and there are other differences as well between k-means and hierarchical. I have shared this. You can read about it. It's not a very difficult things to understand. Okay, now there's another clustering called TSNE clustering. Okay, so in this clustering, sorry, in this clustering, what we do is we take the high dimensional method. Uh, High dimensional means there's some data sets which will not come into the same dimension. Same dimension means, um, okay, what if I have to say, like if you have a similar objects. So if the example I gave you for grass and water, right? So if you take up a pixel of grass, the very much high probability that the nearby pixel of those grass will also belong to the grass category, right? Similarly, if you will take a water pixel, the very high probability that nearby pixels of that water will also belong to the water category, unless the pixel is taken at the boundary of grass and water. Agree to that? That is how we do the TSME clustering. So what we do is we take the neighboring information, like if you are taking a grass pixel, then we are assuming that all the nearby pixels of those grass, like okay, think about a 3 cross 3 or a 5 cross 5 a square, right? So 5 cross 5 square, there will be a middle value of that, right? So that middle value, the nearby information means, uh, from that middle value, the nearby information's values will also belong to the middle value. That's it. I don't know if I'm making any sense. Please let me know if I'm not clear. I'll do something to make you understand this.
Ma'am, the leaf analogy was easy to understand.
Which one?
The grass analogy was
Okay.
easy to understand.
Okay.
Yeah.
That was easy to understand, right? So that is what I meant. Similarly, that is how TSNE clustering is done. Okay. Okay. So I'll show you how. You can read about it if you want. Like one of the unsupervised learning methods for visualization, yeah, it maps high dimensional space into a 2 or 3 dimensional space which can be visualized. Forget about high dimensional and those. Specifically, it models each high dimensional object by a 2 or 3 dimensional point in such a way, yeah, this is line important. Similar objects are modeled by nearby points and dissimilar objects are modeled by distant point with high probability. The example which I gave, okay, it's similar to that. Okay, so I have just these are, you should know just the terminologies. That is why I've kept into it. So TSNE, I'm calling it from sklearn. Plotting again, loading the data set, defining the model. There's something called learning rate. When I discussed about neural network, I have taken the term learning rate. Right? Learning rate is. Can someone tell about learning rate if they remember? Otherwise, I'll explain.
Ma'am, we used it in the back propagation, the eta term.
Exactly, exactly, exactly. So the smaller steps we take, to come to a loss function where the loss function is minimum. That is what learning rate is, right? So over here we have to take a learning rate in TSNE. Why? So for that you have to go for the mathematical terminology for TSNE, and you will see that why learning rate is required. If you want, I can in the briefly I can tell you that what we're doing is we're identifying features with similar features, right? So those similar features, again, we need to take small steps to find, okay, if we'll go to 1 pixel to nearby, it should be the similar. But suddenly if we'll go to 10 pixel of to the pixel you are considering, maybe you can skip and you will go to water pixel, right? So that is why learning rate is important, taking a small step, and those small steps are 100 steps. Okay, so that is why in TSNE learning rate is required. Okay. Okay. So fitting of model, and now plotting. I'm plotting my two-dimension TSNE. So x-axis is 0, y-axis is 1, which I'm considering. Yeah. See the plot. So these, we were having 3 categories. We were dealing with 3 target categories, right? So this is how it is distinguishing 3 categories. But still, 2 categories, which is blue and yellow, are very similar. So we were having 3 categories. Again, I forgot the name. What was that? Sabiska, Vorsinica, and another 3 names were there, right? Okay, where was the names? Target names. Yeah, so we were having Setosha, Virginica, and versicolor, right? So Virginica and versicolors are very identical to each other, the features. So that is why my green and the blue and yellow are very overlapping with each other, while the Setosa purple is differentiating altogether. So this is how my clustering classification can be done.
Madam,
Yeah,
that green and yellow are little bit close to each other. If we want to increase some variance over there, is there any way
yeah, there
so that
are ways. There
it
are
could
ways.
be represented in a nice way?
Yes, definitely. That's what I'm saying. You need to know what kind of data set and what kind of model can work. So that
So
is the most.
in TSNE, can we increase some variance or
Yeah, we
something so
can.
that it is
Yeah,
separated?
obviously we can do that. Either we can increase the learning rate, or either there are different. See, I didn't go much into it because these are like very uh, different clustering algorithm which may not
Yeah.
be used. So obviously we can do that. I have
Okay.
gone with the k means in more detail because k means
Yes.
is very frequently used. So that is where you can see in k means it is very frequently used, and that is where you have to see. Over here I have tried to, you can see I have taken 2 features over here, and both the features are
Mhm.
distinguishable. right?
Ma'am, I asked this question only because that I'm working with some cybersecurity related data set,
Yeah.
and where I'm facing some such kind of issues that data set is almost means when I'm going for clustering, it almost mix up. So
Okay.
to separate them, increasing the variance is the way, or anything else that I want to know actually.
Uh, okay. So to separate the, okay, what kind of algorithm you are using for that?
Majorly, I'm working on the clustering right now.
Yeah, in clustering itself, like there are so many algorithms, right? So you're using
Hmm.
k-means, you're using some other clustering algorithm. Which clustering algorithm you're working with?
I'm working on the K means.
Yeah. So in that way, the most important factor which you have to see is the value of k. So
Okay.
I would suggest you. I don't know what value you are taking for k, but I would suggest you to do a running where you have to see, and
Hmm.
running means hidden trial method. So you have to take different values of k either by increasing or decreasing, and you have to see how your accuracy is behaving along with your
Okay.
error, and then you need to decide a k value, and then you need to do. So the most important factor for k mean clustering is the k value, and then you can go for other factors like variance or correlation or the pca, which I
Hmm.
have done by reducing the dimensionality or taking the
Uh,
important fact features only, something like
okay.
that.
Sorry to interrupt again.
Yeah.
I know that there are five types of different intrusions in my data set.
Okay.
That's why I'm stick with the value like k equals to 5. I'm just giving one example.
Okay. Yeah.
And based on that, I want to make the clustering.
Okay.
Is it the right way or something else I need to choose?
See, here's a trick. The what should be the value of k? There's no thumb rule. There's no thumb
Okay.
rule at all. You
Hmm.
have taken five because you were having five different classes, but it's not necessary. There will be some website or some theoretical places where, and
Hmm.
those are not authentic, I can tell you,
Hmm.
where it has written, okay, however the number of classes you need to take the k value that, but no, it's
Yeah.
not
Hmm.
necessary. The
Hmm.
only way to know what should be the ideal value of k is to know how your accuracy and error is behaving with changing the value of k. So to know the
Okay.
value of k is altogether a work that has to be done if you want to
Hmm.
have your like you would want a good model for your you know data set.
Okay,
So I
because
would
I received one query related with regarding this particular data set,
yeah,
the data set which I'm working.
yeah.
They asked me, you are taking the value for
Hmm.
so many clusters, so that's why I selected 5 as my k value.
Okay.
But still, they have asked me a question. Can
Uh-huh.
you explain? Can you have any trick or any method that you know which by which means mathematically you can say what could be the correct value of k? That was the query I received, and I'm working on that actually. So
Okay.
that way I'm trying to ask you.
Okay. Did you attended my K means class? Like I took, I think two week back. In that,
I think I didn't attend the entire
uh,
lecture.
okay, then I would request you, like, please go to my YouTube channel, and you can or the like this collab notebook which I've
Hmm.
shared for the K means.
Hmm.
I have given the example. I have taken the example how you can select the value of K, with how you can know which is the good value for K. Okay, so I would
Okay.
really request you, because you will get your answer for from that. I feel like you can get the answer from that
Yeah,
notebook
sure.
of mine.
I will go
Okay.
through it.
Okay.
Thank you.
Thank you. Okay, so moving ahead to the last clustering, which is the Baskin clustering, which is density based. The full form of DBSCN is density based spatial clustering of applications with noise, which means it's basically this clustering came into picture when our k-mean has disadvantage as well. So when there is noise in my data, what does noise means? For example, we were taking example of grass and water pixels, right? But what if somehow soil pixels come into the picture, or if there's a butterfly, that pixels come into the picture? You cannot classify the butterfly as grass itself. You knew just two features, right? So that butterfly pixel will be an outlier or a noise which you need to remove. So K means, because there are three classes now. So K means have disadvantage over there when there's a noise in the pixel. Okay. So that is where this DBSCN was introduced. So what it does, it doesn't take the number of cluster, but it take two different parameters, two different kinds of parameter which needed to be tuned, which is, and two different parameters it taken is called the distance basically. So one is the EPS parameter, which is the maximum distance between two data points to be considered in the same neighborhood. And there's another called minimum sample parameter, which is the minimum amount of data points in the neighborhood to be considered. So I would request you to read these two lines. You will understand what I'm saying. These are the two parameters which is required by DBSCM. Okay. So based on that, it doesn't take the clustering how my k-mean was depending on the number of the value of k. It just take these two parameters and then do the classification or then do the clustering. Okay. So again, I have imported this DBSCN, and over there I need to take the PCA because it's not required for this data set, but for a lot larger data set, there's very much requirement of PCA. Okay. And loading of my data set and declaring my model, fitting it. Now I'm transferring my PCA, which means I'm taking how many components I want to take. So I've taken two components, and then I'm doing the this clustering. See, this is how it have segregated all the two clusters because I have taken PCA, right? So since we were having three features, but with PCA we just took two features, right? So we just took two features and it is segregating this green and red. And these stars, which is blue in color, are noises. So it is segregating noise as well. So if the example which I took for grass and water and a butterfly, so the blue will be represented as butterfly and other two will be represented as classes. So DBSCN was able to do as this as well. Two classes and a noise. Okay. So okay. So this was a lecture for unsupervised learning with different clusters. I have already shared the Google Colab link, and if someone have joined late, I'll suggest just copy paste it again. So we stop presenting. Okay, so do you guys have any questions? So let me know, and just go through these clustering algorithm. And those who have doubt, like I would request you to again go to the key mean clustering algorithm, which I handled. That was both for classification and regression, and you may get your answer what you're looking for. I'm hoping for that. Okay, and the next two classes I try to take the graphical modeling, which is more of like Markov random field and other graphic method. Okay.
Okay, madam.
Okay, then see you in the next class. Thank you.
Thank
Thank
you.
you, ma'am.